Welcome to our introduction to hypothesis testing. Today we will look at the logic of this procedure. The following slides will guide you through the steps of this inferential process.
Hypothesis testing is a structured process that you will use throughout the remainder of the course. Hypothesis testing is a four-step process. We're usually concerned about a population parameter, so step 1 is to state the hypothesis about a population. Step 2 is predict the characteristics of the sample based on the hypothesis. Let's say that an American adult gains an average of 7 pounds between Thanksgiving and New Year's Day. We would predict that a sample taken from this population would have a mean of 7 pounds. Step 3, we take a random sample from the population. And step 4, we compare the sample data with the prediction made from the hypothesis. If the sample mean is consistent with our prediction, then the null hypothesis is reasonable. If the sample mean is greatly different from our prediction, then we decide the hypothesis is wrong and we reject it. From the point of view of the hypothesis test, the entire population receives the treatment and then a sample is selected from the treated population. In actual research, a sample is selected from the original population and the treatment is administered to the sample. Step 1. State hypothesis. The first step is to state the problem. This is our educated guess about what is really happening. We can state it in two different forms. The null hypothesis states that there is no effect or no change. The null hypothesis states that the mean for the treated population is the same as the mean before the treatment. The alternative hypothesis is the exact opposite of the null hypothesis. Step 2. Set the criteria for decision. The alpha level, usually alpha equals 0.05 or alpha equals 0.01, provides a definition of the term very unlikely and determines the risk of a type 1 error. The critical region is defined as sample outcomes that would be very unlikely to occur if the null hypothesis is true. For example, with an alpha equals 0.05, the critical region is defined as the sample means in the extreme 5% of the distribution of sample means. When the distribution is normal, the extreme 5% corresponds to z-scores beyond plus or minus 1.96 for two-tailed tests. I often call the critical region the rejection zone because if a value falls within that area, you have evidence to reject the null hypothesis. This figure shows a normal distribution showing the likely and unlikely values to occur if the null hypothesis is true. Step 3. Collect data and compute statistics. To have objectivity in your study, the data is only collected after the hypothesis is stated and the alpha level for significance has been set. After the data is collected, the sample statistic is computed. The sample mean is transformed into a z-score. The z-score test statistic identifies the location of the sample mean in the distribution of sample means. Step 4. Make a decision. If the obtained z-score, the value calculated from the sample data, is in the critical region, reject the null hypothesis because it is very unlikely that these data would be obtained if the null hypothesis were true. Conclude that the treatment has changed the population mean. If the z-score is not in the critical region, fail to reject the null hypothesis because the data are not significantly different from the null hypothesis. In this case, the data do not provide sufficient evidence to indicate that the treatment has had an effect. Using sample data to draw a conclusion about a population means that errors are possible. Whenever a decision is reached in a hypothesis test, there's always the risk of making the incorrect decision. There are two types of errors that can be committed, type 1 and type 2 errors. Type 1 error occurs only when the null hypothesis is true. A type 1 error is defined as rejecting a true null hypothesis. This is a serious error because it results in falsely reporting a treatment effect. The risk of a type 1 error is determined by the alpha level and is therefore under the experimenter's control. For example, when p is less than 0.05, there's less than a 5% chance that we will commit a type 1 error. Type 2 errors only occur when the alternative hypothesis is true. Type 2 error is defined as the failure to reject a null hypothesis. In this case, the experiment fails to detect an effect that actually occurred. The probability of a type 2 error cannot be specified as a single value and depends on part in the size of the treatment effect. It's identified by the symbol beta. When reporting the results of a statistical test, it should include a statement of the significance, the value of the test statistic, and the alpha level. For instance, we may read, the new supplement had a significant effect on cognitive skills. Z equals 2.53, P less than 0.05. The statement tells us that the null hypothesis was rejected. The value of the Z statistic used to evaluate the sample data was 2.53. It also tells us that the alpha level was set at 0.05, so the possibility of a type 1 error was 5%.
I hope the previous slides have given you some information to use with future inferential statistics. We will use the same steps with other hypothesis tests, such as t-tests, ANOVA, and chi-square.